Thank you very much for inviting us to present today. As Seb said, we are going to be talking about sort of the geological works on East West Rail and sort of their engineering impacts as well. Just a bit of a brief agenda, a bit of an introduction to the project and ourselves. Then we'll go into the actual geology of the site, and then Simon will pick up with the geotechnical engineering solutions. Then we'll finish with a bit of a Q&A. So, yeah, my name's Kate Kendall. I am an engineering geologist. I've been at AtkinsRéalis now for nearly 8 years. My involvement with East West Rail started back in 2016 when I was a graduate. And I've had several different roles on the project. I've spec'd and supervised a ground investigation, done some of the interpretation work as well, also moved into trackbed design, and more recently I spent 3.5 years out on site supervising the GI and as part of the site delivery team as site engineer and as the section engineer, working with the contractors doing the construction of the earthworks, trackbed and drainage. Just hand over to Simon so he can introduce himself as well.
Hello, I'm Simon Miles, Chief Geotechnical Engineer with AtkinsRéalis. As the slide says, I've been there 26 years, but I was on East West Rail Phase 2 only since 2021, when I was brought in to help ensure that the earthworks were delivered on time, which in that sense meant within one earthwork season. We did do that, but since I was there, I did assume a few more responsibilities. So we started to look after trackbed installation. Most of the geotechnical type design changes came my way. There were a few engineering challenges that we needed to look at, and we'll come on to those a little bit later on. And just latterly, we've been looking after the geotechnical asset handover back to Network Rail. So back to Kate.
Great, thank you very much. So just a bit of a project overview for those who don't know about East West Rail. The overarching East West Rail project is reconnecting Oxford to Cambridge. We're focusing here on Phase 2, which is the section between Bicester and Bletchley. This is split into 3 areas, 2A, 2B, and then 2C, which is just around the Bletchley end, which is the Milton Keynes end of the project. A and B are sandwiched with the HS2 integration area, as HS2 comes up from the London direction. In terms of the works, the permanent works consisted of about 1 million cubic metres of earthworks, almost 70 kilometres of track and drainage. There was also 2 new stations and a lot of bridge work as well, with 5 new overbridges, footbridges, and refurbishment of a number of existing bridges as well. There's also the rebuild of the Bletchley flyover and 130 kilometres of new fencing. Now, to facilitate that permanent works, a lot of enabling works went into the job as well. This includes permanent and temporary land take to facilitate that construction. And then you've also got all the construction logistics, which I'm sure you can imagine was quite a lot. So there was 12 construction compounds and a lot of highways intervention works around the nice countryside of Buckinghamshire and Oxfordshire. In terms of the project programme, pre-2019 is when AtkinsRéalis were largely starting to get involved with the project. We began at sort of GRIP 4, so single option development stage, and then moved into GRIP 5, detailed design. During 2019, design was still ongoing, and it was a commencement of the early works. So that sort of involved land purchase, works on the highways around the sites, and starting on the D-Veg works along the track. Following the Transport Works Act order in 2020, the civils works could properly start on site. So that involved everything: trackbed, earthworks, drainage, new structures, everything and anything that was needed to allow for the track to then be laid, which commenced mid-2022 in Section 2C and has been continuing since then. We are now at a point where all track has been completed. HS2 handed over their section at the end of last year, and we're very much just on the SP&C, so signal, power and comms installation, ready for handover to Network Rail, and infrastructure ready end of this year, with, I believe, a view to open next year. So just a few general photos of where the project is at the moment. As you can see, it very much looks like a proper railway, and all the track has now been installed. So yeah, 66 kilometres of track. And there was, you might have seen stuff on LinkedIn recently, there was a big sort of formal handover and last bit of track going in the last few weeks. This is just a very quick side-by-side drone video, actually, showing the progress of the works, just to give you a bit of an idea about how everything progressed from 2021 through to 2023. I wasn't expecting the loud music. This is the Bletchley flyover. So this is one of the new stations in Bletchley, and then it moves into the flyover, which is over the West Coast Main Line. You can see how the work sort of progressed quite rapidly. This is one of the new overbridges. So we had to remove the bridge you can see at the bottom and construct a new overbridge. This is one of the packages of work I was heavily involved with the construction of that embankment. This is Winslow Station, so the other new station along the route. Very much just regrading of slopes and starting to see sheet piles. And then 2 years later, we very much got the platforms and station virtually finished with a new footbridge as well. You can see in the top right corner, you've got one of our construction compounds as well. So this is another one of the refurbed bridges. Another overbridge. As part of the project, we had to remove all level crossings. So this was an overbridge to facilitate farmers' access to his fields. It's quite a large structure. This was a new bridge deck and bridge refurbishment. And another overbridge again to remove the requirement for level crossings. And another overbridge you can see just in the top where the level crossing an existing road is, which has now been diverted onto that new structure. And then this is the most western end of the project at Bicester. You can just see how everything has developed in 2 years through the main construction phase. Right, now moving on to what we're probably all here for is looking a little bit at the geology of the site. Now we've done a bit of where we are and what the project is. So East West Rail Phase 2 between Bicester and Bletchley. The geology of the site is an age range of sort of mid to late Jurassic. The site very much, we encounter all of this. We start with the youngest West Walton Formation, which you can see down towards the Bletchley end. This, from BGS mapping and literature, is described sort of silty mudstone with interbedded calcareous mudstone and is regionally reported at 10 to 15 metres thick. This then moves down into the Oxford Clay Formation, which in total in region is reported to be about 60 metres in thickness and is split into 3 different members: the Peterborough member, Stewartby member, and then down into the Weymouth member. Within sort of the memoirs and the general regional descriptions of the site, these members are differentiated. However, and I'll touch on this a bit further, we, as part of our interpretation work, group them into the one formation. Then move down into the Kelloways Formation. We've got the Kelloway Sand member up to about 5 metres thick, which is quartz sand silt mudstone, and then down into the Clay member, which is sort of 1 to 4 metres thick. And again, sort of this one's a bit more of a pyritic mudstone. At the base, and you can very much just see it slightly outcropping at the Bicester end, is the Cornbrash Formation, which is a waxstone, packstone, with some layers of calcareous mudstone within it, and that's sort of recorded at 1 to 4 metres thick. So it's quite a lot of clay bedrock across the site of Jurassic Age. Moving into the Quaternary geology, the site very much lies at the reported most southern extent of the Anglia glaciation, which is about 350,000 years old. The BGS mapping shows the glacial deposits very much to the east of the site, particularly around the Winslow area. You can see the light blue and the pink is glacial till and glacial fluvial deposits, which sort of very much map that extent of the ice sheet. There's also across the site alluvium and river terrace deposits, which are attributed to the tributaries of the River Ouse in the area. And so, yeah, across the site, particularly from section 2B and 2C, we've got a lot of quaternary and superficial geology that we needed to think about and understand as we sort of went into the design phase. Just want to quickly touch on the fact that we are rehabilitating a historic railway and the importance of that in how we take the geology and look at also more recent activity. These are just a few photos from when I sort of started out on site in 2018. But rehabilitating a railway sort of does have its own unique challenge. For this site, the mapping generally shows that the railway was present from the sort of 1840s. But the majority of the route was then closed to passenger traffic in 1960s as part of the beach enclosures, with then the vast majority, especially section 2B between Calvert and Newton Longville, closed completely in the 90s, which is why very much, well, it was before that actually here, but it very much is overgrown and very different to what you'd expect to see. Historic construction methods of railway meant that we need to not only understand the underlying geology, but also the construction material of the embankments and the slope stability of the cuttings and the embankments. And alongside this, we needed to understand how the track bed had been constructed and how we could then remediate that or replace it so we could meet modern standards for track stiffness. A few more photos of what it looked like, but construction of historic railways didn't follow a design based on the soil mechanics and standards that we employ today. Mostly to meet sort of time and efficiency constraints, embankments were constructed by end tipping of material, so they literally just dump material at the advancing head of works, and a lot of it will have come from cuttings that were created. This is something that we did very much see. You've got a lot of reworked material forming the embankments here. And there would have been no preparation of the grounds before placement. So no compaction, no removal of topsoil, nothing like that, just dump straight on. Again, this is all something we had to bear in mind moving forwards through the design process. So where we sort of begin, the ground investigation, we needed to build a ground model to inform the earthworks assessment, bridge foundation structures, and also trackbed design. We also needed to verify the BGS mapping, identify geotechnical parameters, and that were required for the design and stability assessments. Now, we had a GRIP 3 phase of GI that had been done prior to Atkins undertaking and starting on the work as part of the Alliance. That was predominantly sort of evenly spaced boreholes. As you can sort of see on here, there's a lot of there was a high number of boreholes, but they were evenly spaced along the existing earthworks. So we took this, did a gap analysis, and then focused in and targeted structures, areas where there might be instability that we've picked up on walkovers, and also further investigation to inform the trackbed design because there hadn't been anything specific for that. So during GRIP 4 and GRIP 5, you can see we've massively increased the amount of investigation work that was done. You've got to remember that this is 40 kilometres in length. It's quite extensive, and we do cross varied geology and varied thickness of superficial. So we need to have a really good idea of what we were building on or building within. You probably noticed the trial pits of a number of us increased dramatically. Trial pits were used along with some automatic ballast sampling for the trackbed investigation works because we needed to know exactly what we were building on in terms of that sort of top half metre. Window samples were generally targeting the earthworks, and then we have additional sort of dynamic sampling, rotary coring for around sort of the structures and anything we needed to get that bit deeper for to understand for foundations. There was also some geophysics done. I'm not going to go into too much detail or any detail at all on this. It's not my area of expertise, but just more to highlight that we did use some of those investigation techniques, particularly around where new approach embankments were going to be built, and also trialed some GPR to, again, help inform some of the trackbed design. There's also monitoring undertaken. Inclinometers were installed as part of GRIP 4 and GRIP 5 to monitor where instability had previously been noted during these walkovers that we did in the early phase. And then also a full suite of sort of groundwater and ground gas monitoring, as well as some vibrating wire piezometers to build into our ground model. The ground investigation that we did was over a number of years. So it was between July 2017 and September 2020, which was we were doing it throughout doing the design as well. So it was very much the investigation started, then started to inform the design, and we were building on it as we go. Challenges of doing a ground investigation on a former railway, you very much got the location. They're all very different. We range from greenfields to mothballed railway, access points, different times of year, very, very different conditions underfoot as well. So we needed to constantly be assessing how we were going to get drilling rigs and equipment to the locations, as well as obviously we've got some slight land take. We're very in the edge of a farmer's field there at the top of a cutting. So it was all trying to get the best information we could out of quite tight restrictions in some cases. Also, what's important to remember is that there was such a variety of design requirements for this job. For example, these two photos we've got, this is Bletchley, where the new high-level platforms have gone. So this is for pile foundations. And then on the right, you've got the window sample rig, which is looking at the earthwork. So being out there and supervising for me, I had to make sure that I knew exactly what each hole was for. And that's something that I very much try and instill on others today. You need to know what it's for, because in case you have to make on-the-ground decisions to change any sampling, testing, increase the depth of hole, etc. So it's always good to be aware of that. And then there's just a couple of the photos that did see some sort of interesting stuff. So we've got nice ammonite there. This was in Bletchley. Middle photo is actually at the location of the farmer's field, a couple of slides back. And then this is Winslow on the far right, which just shows the sort of conditions we were working in. And yeah, trying to get a drilling rig out there, it was quite wet as well. Once we had all our information, it was then a case of looking into the interpretation side of things. Ground models and GIRs were split into the three route sections, and each report provided an overarching summary of the section and the geology of the route. Also looked at the parameters that were derived for the geology and the geological strata in that area, and a preliminary assessment for earthwork structures and, if required, the stations. We produced these geological models which had the mapping at the top showing the borehole location and some fantastic modelling at the bottom. I can take no credit for that. It was a big team of people working on these behind the scenes. I just wanted to sort of include a couple of snippets of some of the logs that we were receiving. One in the top corner actually sort of shows what I was talking about before. We've got a 6-metre embankment there, and at the bottom of that is relic topsoil. So it just hammers home what I was sort of saying before about that historic construction technique of just literally tipping material on the ground. Putting the parameter derivation aside briefly, it's also important to note the strata encountered and its thicknesses compared to what I sort of mentioned before about the regional geology, and how obviously the importance of a ground investigation to confirm that specifically for your site. You can sort of see from this, the thickness of the glacial material was hugely variable, which is probably not to be unexpected due to the general variable nature of the glacial material because of its manner of deposition. The thickest deposits were between Winslow and Newton Longville, which is exactly sort of where we anticipated that southern extent of that ice sheet. One of the key outcomes of the interpretation, which I sort of touched on earlier, was that we did group the Oxford Clay Formation based on and this was because of the sort of the strata descriptions. It was very difficult to differentiate between varying levels of grey clay, and the parameters that we were deriving, there wasn't a distinct variability between them. And so for the purposes of what we needed for design, it was deemed suitable that these three members should be grouped together. The glacial deposits were also separated into granular and cohesive, purely different. We're talking different material types. They perform very differently, and we need to know exactly how those are going to perform when it comes to sort of the parameter derivation and feeding into our design work. Another thing that we did also identify, I mentioned earlier that we very much only were expecting glacial material in section 2B and 2C, but as part of the investigation work, we did identify some pockets of glacial material further west on the job. So this is just an example where we've got the BGS mapping at the top, and with the ground model at the bottom, you can see that we have picked up some quite extensive pocket of glacial, cohesive glacial deposits. So again, just sort of reiterates the importance of ground investigations, ground modelling, and building on that original desk study. The interpretation work that was done and the parameters derived as part of the GIR sort of were all used to inform permanent works, but I also use them very much on my site role job to inform temporary works designs that we were doing alongside, and then we'd do additional testing on site to verify those. The investigation work never targeted where we were going to need temporary works. So I would take the GIR, take the ground models, understand what material we were expecting, and then go and just test and confirm that on site. So this is just an example of where I needed to produce a platform for a mobile working platform. So I needed a stable ground surface basically for it to work on. Had the original ground model, fed that in here, understood what material we were anticipating and its strength, and then did some DCPs just to verify that on site. So just a case of remembering that it's not just permanent works that we're doing all this for, it does feed into the temporary works as well. And on site in East West Rail, we were lucky enough to have a UCAS accredited lab in one of the compounds. So we use that quite regularly for sort of basic geotechnical tests, sort of PSDs, Atterbergs, that could then be used throughout the construction process to verify the information that we were finding. So that just sort of gives you a bit of a brief overview of the geology of the site, the materials we encountered, how we went about developing the ground model side of things. Simon's now going to touch on a bit more about the engineering solutions and challenges that we faced. Thank you.
Right, so that was the interesting bit. Now for the engineering. I'll take you back in time a little bit. I've already told you that I started the project in 2021. But before detailed design started, the Secretary of State set a challenge because it was too expensive. We've heard that before. But anyway, as part of the Secretary of State's challenge to bring the cost down, there was a track alignment value for money exercise, which meant the alignment was raised a bit in the cuttings and lowered a bit on the embankments. And there was a few horizontal adjustments just for impacts, to minimize impacts on third parties. But raising the alignment in the cuttings and lowering it on the embankments meant we had to do so much less intervention on the slopes because we basically widened the platform that we had to play with. So reducing the cess level was only 520 millimeters, which isn't very much. Similarly, raising it in the cuttings is actually only 75 mil above rail, but it did make a difference. Also, a significant difference made by reducing the offset to the drainage from 2 meters to 1, which obviously reduced the footprint. The construction methodology was completely turned upside down. Originally, the haul roads were going to be on temporary land take outside of the trace, and they were all brought inside the route, and we used the track bed as the haul road. Also, originally, the whole route was going to be electrified. Obviously, that got cut out, which meant that interventions on the structures could be changed as well. And quite a lot of the structures went from being completely rebuilt to just being refurbished or slightly altered. And the earthwork task and finish was brought in quite considerably. I think the original program showed it taking 4 years. I've already told you we did it in less than 18 months. As part of that, there were a few design principles written down and adopted. Clearly, with an old railway line of 150 years old or more, it's completely impractical to apply Eurocode and expect it to comply. You just can't do it. So the approach that was taken was that for any part of the route that was not what Network Rail would deem an earthwork, i.e. about 3 meters high or less, we applied a no worsening approach. So long as the serviceability limit state didn't get worse, crack on, get on with it. For earthworks, on the official definition, if the design was such that a serviceable earthwork, as defined by the standard 71, was not made worse, then that no worsening approach carried on. Sorry, it didn't. Betterment approach was adopted for that, which meant the fracture state had to get better by 5%. For marginal or poor earthworks, then clearly we needed a bit more intervention on those, and we actually went for EC7 compliant intervention, which meant basically a slope regrade. The classifications, poor, marginal, and serviceable, are those in the earthwork hazard classifications of Network Rail standards. And that's all I'm going to say on that. Now, cuttings and earthworks, slightly different. So if in the embankment case, the proposed works do not impact the existing slopes, then so long as the earthwork was deemed to be serviceable or even marginal, the slopes were left untouched. In the marginal case, so long as you could prove there was no worsening. If it was deemed to be in a poor state, then it was given a design with 5% betterment. If the proposed works did impact the slopes, then the serviceable ones got 5% betterment and the marginal and poor ones basically got reconstructed. For a cutting, slightly different. So if the proposed works didn't impact the slopes, as long as it was serviceable or marginal, we left the slopes alone. Again, provided that no worsening could be proven. If it was poor, it got 5% betterment. Where we did impact the existing slopes in the cuttings, serviceable slopes got 5% betterment, marginal or poor ones got reconstructed. This job was probably one of the more digital ones I've worked on, both through design and into construction. So this slide just gives a kind of overview of what digital tools we had. So the track bed design summary sheets were done through a macro in Civil 3D, combining the GI and track bed investigation data from whole base, the vertical alignment data from the surveys, and the track bed condition treatments from the design to come up with a summary, a big summary sheet. The whole job was modeled in iModel, Bentley iModel in 3D. So every single thing that got designed was turned into a 3D element, which was combined and came up with these fancy models that you could drive your way through and see how things fitted together. And during construction, the plant that was out there building it was actually controlled by service levels and strings and 3D gizmos so that they're always in the right place. So, track bed. The scheme is scoped to provide 100 mile per hour dual track railway from just west of Bletchley to Gavray Junction at Bicester. And to do that, we need to provide a subgrade stiffness sufficient to support the track to support that design speed. Standards determine the required dynamic sleeper support stiffness and the ballast depths, and they combined give us the required treatments for the foundation layers. Depending on what the track bed investigation told us, we've got treatments varying in thickness from 150 mil to 650 mil, all of them with at least one layer of geogrid in them, which will reduce the depth that we needed to provide. One thing we quickly realized, and we should have realized before, was that it's an existing subgrade. So it's quite stiff at the top before you start messing about with it. But when you start putting your treatments in, if you dig through that stiff layer, it does actually get softer as you go deeper. So what started out with a design treatment of, say, 150 mil, but with the in-situ testing was proved to be too soft for that, we probably ended up quite a lot deeper than that because it just got softer. I'll go into a little bit later, but that track bed, because of the Secretary of State's challenge, also had to act as the haul road. And to protect it, for the final design, it was given an extra 150 mil of type 1 on top as a running surface. So this diagram shows how that was done. So essentially, for the design subgrade, we designed a track bed treatment and we designed a haul road, and we combined them together, and what was actually built was the thicker of the two treatments, and then added 150 mil sacrificial on top. So we knew it was designed to carry the construction traffic, and we knew that once we'd stripped off that 150 mil of type 1, it was adequate for the permanent railway. So track bed treatments were determined by design and confirmed by on-site DCP testing. I've already said, range between 150 and 650 mil. There's 250 millimeters of bottom ballast to go on top of that before we put the track on. And obviously transitions to structures, because we don't want sudden changes in track stiffness, are treated separately, and we get a gradual transition onto the structures and off them again. The installed track bed was then subject to confirmatory stiffness testing with a target formation stiffness. We quickly realized again that if you test them straight after you've laid it, you'll get a much worse result than if you leave it for a week. I'll leave you to figure out why, but if you can't, ask me later. Okay, and I'll just run through a little bit about the earthworks and such. So these two pictures are both of the same cutting, as it happens. Both show full height regrades, in this case through Winslow Station. So these are going to provide a full Eurocode 7 compliant design for what were at the time deemed to be slopes in poor condition. And they give an idea of how much intervention we sometimes had to provide. Lower cuttings, these are not Winslow Station, but somewhere to the west, give examples of partial regrades, which is in effect 5% betterment. These were poor slopes, but the corridor itself doesn't impact them. So all we had to do was essentially tidy them up. Embankments, slightly different. So the top photograph shows a brand new embankment where the horizontal alignment of the railway was altered to possibly increase line speed onto the viaduct. But that is fully Eurocode compliant, as befits a brand new asset. The bottom photograph shows a CES regrade, a 5% betterment solution for a serviceable embankment. But on the other side, you can see where there wasn't room to do a slope regrade or anything to do with the slopes, we actually had to put in a CES retention wall. And there's quite a lot of those on site. In the structures, the existing structures were all assessed for stability engaging for the new alignment and allowance for electrification, even if we're not going to put it in just yet. And depending on the answers, they're either left as is, demolished and replaced, strengthened, or lifted. The photograph top left you may recognize from one of the photographs that Kate showed you earlier is OXD 10A, which was in such poor condition it nearly fell down, never mind taken down, but we did demolish it. And the photograph's taken from its replacement. Top right is OXD 29, which was strengthened by arch infill. And the one bottom right is, I think, OXD 25, which had its deck replaced with con arch units. The new structures generally piled with precast shell abutments. In most cases, the piles went into Oxford clay and acted in skin friction. The one shown, top left, is actually 36AA at Bicester and is piled onto the Cornbrash limestone. At the bottom, it is Verney Junction Overbridge, the Farmers Access Overbridge. It's the largest accommodation bridge I've ever seen, but is also the only bridge that isn't piled. That one was built on 3 meters depth of excavated quaternary deposits replaced with engineered fill, and then a reinforced earth abutments. So the superficial deposits were entirely removed, and it's actually founded on the Oxford clay. Now, I did mention earlier we had a few engineering challenges. If you're in here earlier watching the photos go round and round, you'll have seen this one. We're in the midst of putting in a retaining wall at the bottom of this embankment when the slope next to it, after a period of quite heavy rain, decided it wasn't going to stand up anymore. So that one failed during construction. We did a little bit of digging around, sometimes literally, found signs that it had actually failed before because there were grout inclusions within the embankment. And there's some evidence that there was actually a train derailment at that site about in the 1950s or so, which may have something to do with this, may not, I don't know. Anyway, what we did for that was we actually extended the wall and slackened the slope. Another one, we had a seepage in a cutting slope. Persistent, wouldn't go away. It was threatening the stability of the earthwork, so we clearly couldn't leave it because Network Rail would never have accepted it. And we deemed it to be a shallow subsurface flow from the uphill catchment, which is, it goes back quite a long way from the top of the cutting. So we didn't do anything too clever. We just dug a big ditch, basically, filled the bottom half with gravel and basically constructed a cutoff, which then went into the track drainage a bit further up drainage. Track bed. Now, I mentioned earlier, every piece of track bed that we put in was subject to confirmatory stiffness testing, which it was. To start with, we had a spate of those confirmatory tests failing. So we did some trials in one of the compounds, and we couldn't get consistent results out of those either, even though, you know, they were built on firm ground, done really carefully, and we still couldn't get consistent results. So we delved a little bit more into the standards and found out a few things. So the original specified stiffness was 45 megapascals. We generally couldn't get near that, but we could get over 30. A review of the standards requirements did reduce this to 30, as measured by LWD. But we had to get this through Network Rail, obviously, so we had to explain ourselves. There are two standards that apply. So 2102 requires a formation stiffness of 45 newtons per meter. And 4239 requires a dynamic sleeper support stiffness, okay, of 60 kilonewton per millimeter per sleeper end. But in a note to a table in small print says, you can reduce this to 30 kilonewton per millimeter per sleeper end if you include geogrid reinforcement. And it also says somewhere else that a K of 60 is equivalent to a formation stiffness of 30 megapascals. So very careful reading of the standards shows that our track bed treatments, which include geogrids, are equivalent to requiring a stiffness of 30 megapascals, not 45 as we originally thought. So the interpretation of the standards say formation stiffness has to be 45 newton per meter was wrongly converted to 45 megapascals, and it should have been 30. And once we changed the standard and changed the specification, we had no more problems. That paragraph on the bottom gives you the answer to the question I posed you a little earlier on. Testing immediately after laying the trap bed generally gave a lower stiffness because there was excess poor water pressures in it generated during the laying and the compaction. And if you let those dissipate, then you'll get a better result, which is obviously the long-term result, which is the one we want. We did get a problem with settlement of a bridge. Obviously, it was the bridge that wasn't piled, the one that was sitting on 3 meters of engineered fill. The design assumed, is the word, that both abutments would be built simultaneously and that they would be built in 63 days. Unfortunately, that wasn't conveyed to the contractor, either of those points. So we built them at different times, in fact, 60 days apart. But that isn't really the nub of the problem. The problem is that they settled and they kept settling and they kept settling and they kept going. We did some CPT investigations to try and figure out why it was so different to what our design assumptions had been. And in fact, those investigations proved the ground model to be exactly as the design said it was. So we're none the wiser, really. However, we did delay construction of the bridge. We delayed putting the deck on for 5 months whilst the settlements dissipated and evened out. Eventually, it got to the point that both abutments settled at the same rate, at which point we said, well, the differential settlement's nil now. I mean, it might still be going down, but at least it's going down at the same rate. So we put the deck on and then left it a bit. And eventually we concreted it in and finished the bridge. And eventually the settlements got to the point where we could stop monitoring it because it was going down by a fraction of a millimetre a month, almost nothing. Another bridge, you've seen it before. This one was stabilised by infilling the side arches. Originally, before the Secretary of State's challenge, it was going to be underpinned. 15 months after it was strengthened, one of the engineers walking by, who was actually there to look at the stability of the cutting slopes, noticed that some cracks had started forming in the structure. And he raised it. So a few days later, we went out and said, "Ooh, they're big." So we put some monitoring in place. There were cracks through the sidewalls of the main arch. There were cracks in the spandrels and the parapets. There were cracks all over the place. That monitoring was in place for some months and showed those cracks were gradually getting bigger and bigger. So it was clear we couldn't leave it. So the strengthening that had been put in place consisted of lightweight concrete in the side spans and a new concrete saddle deck across the top. There was no indication that the saddle deck was in distress at all. There was some indication that the lightweight concrete maybe wasn't quite as light as it should have been. And there's also some indication that it didn't fill the arches up quite as much as it should have been. But nevertheless, this structure was in some distress and we had to move quickly and do something about it. So it was observed 12 months after the trap bed works and 15 months after the completion of the bridge strengthening. We thought maybe it was an old circular slip that had been reactivated. Maybe. May also have been a wedge failure caused by failure of the foundation on the concrete infill. We don't know. I mean, obviously we didn't take the bridge apart to find out. We did come up with a design to fix it. We put in 6 inclined ground anchors, 24 meters long, into the Oxford clay, both sides, to basically tie that arch foundation back into its actual foundation. And there are 7 inclined mini piles underneath the capping beam as well, which take the vertical component from those ground anchors. We considered that the foundation, the original foundation of the bridge, was not capable of taking any extra load, and we didn't want to try it. It's also worth noting that as part of these works, we did find out where the bottom of those foundations were, and it's roughly where the track bed is on that photograph. It's really not very deep. So it's not surprising that it was in a bit of distress. But anyway, we put all that in. We continued monitoring for a little while just to make sure it stopped moving, and it hasn't moved an inch since, hasn't moved a millimeter since. So that's it, really. And that's my favorite photograph, the one I took. Any questions?